Alright, kiddos, this is a colligative property. So it says chapter 13 and 14. If you have the online book, this is chapter 13, it's into chapter 13. If you have an old blue hard copy of a book, the old blue hard copy, those are the pages out of chapter 14. So this is called colligative properties. They're good problems. They are the next thing in line for us if we were at school. We're using our smartboard / pieces of paper that I printed out slides on. It's like projecting right on a board. I can write on it. So here's the definition of colligative property. Colligative property is something that depends on the concentration of the solute particles, not the identity of the solute particles. So it's about how much stuff we're adding to the solution. It's not about what the stuff is. And so we are going to add solute to solvent, add stuff to the solution, and when we add stuff to the solution, we're going to look at how properties are affected by that. So if you need to look at that for longer, pause that thing and you can go through it. We're probably going to do this in 2 chunks. I'm going to do just the conceptual part here in a 10-minute video, and then we'll come back and do the workout problems in the subsequent video. So there's the definition of colligative property. There are several colligative properties. We're going to talk about 2 of them here, and the 2 we're going to talk about are these 2: freezing point depression and boiling point elevation. So what this says, colligative property wise, is if you add something to a solvent, then you are going to cause the freezing point of that solvent to decrease. If you add something to the solvent, you cause the boiling point to increase. So it doesn't matter, again, what it is, it's how much of it is dissolved. So if you add something to water, the freezing point of water that was 0 in pure form is now going to be less than 0. You actually lower the freezing point. And in boiling point, if you have pure water, it boils at 100. If you add something to the water, it doesn't matter what it is. If you add dirt to the water, or you add salt to the water, or you add your hand to the water, it is going to increase the boiling point. Don't add your hand to the water. You can see what the new boiling point is. It'll be uncomfortable. So these are the 2 we're going to talk about. So freezing point depression and boiling point elevation. You'll see this notation when we do the problems. It's delta T, change in temperature of freezing, and change in temperature of boiling. It will matter whether you're talking about freezing point depression or boiling point elevation, because there are constants, and the constants are different whether they're freezing or boiling. Good. So the first one here gives us the freezing point depression idea. And so what happens is when you have water forms this hexagonal structure that looks like this when it freezes, when it turns into ice. So this is part of the reason that water is less dense as a solid, is because when these hydrogen bonds happen between these water molecules, they create space in there, so there's space in between. When we're talking about freezing point of stuff, this is the normal shape water would freeze in. If we add stuff to the water, so every one of these water molecules is surrounded by 3 other water molecules by their hydrogen bonds, and so they're connected to each other this way. When you add something in between, whether it be dirt or salt or mud or whatever, when you add something in between, all of a sudden this hydrogen bond that was connecting these 2 is no longer there, which means these particles are struggling more to hang on to each other. And the more stuff you add, the more and more of those hydrogen bonds that get disrupted. And in order to get this guy to stay moving slowly, and to stay frozen, to stay in that position, you have to slow him way down, because now he's only got 1 hydrogen bond that's holding him. And so he has more freedom of movement. I always talk about it with the analogy of police officers, right? If this is our criminal here, and they've got 3 police officers holding on to them, that criminal's not going anywhere. He's locked into that fixed position. But if you look over here, this police officer trying to hold the criminal, if we put stuff in the way, right, and there's only 1 police officer now holding on to that criminal, then that criminal can get away. And so what does that police officer have to do in order to keep that criminal from running? It's harder to hang on to him because he can move faster when there's only one person hanging on to him. So what does that police officer have to do to him in order to control that, or in order to keep him in a fixed position? You could say a lot. I always get tase him. Tasing him would be good. What does tasing do to that criminal? It slows that criminal down, so that criminal can stay locked in that fixed position where that cop can now control that criminal, or he can put ankle cuffs on him so that criminal slows down. If you can slow him down, you can keep him in a fixed position. You can keep control over him. And it's the same idea here. The more stuff you add in between those water molecules, the lower and lower the freezing point has to be in order to hold those things in fixed position. You have to slow those particles down. And as we've talked about before, lowering the lowering the temperature is going to cause particles to move slower, and you can hold them in those fixed positions for longer. Hopefully that kind of makes sense, but that's the idea. And it doesn't matter what you add, right? You add a shoe in there, that shoe is going to disrupt some of those hydrogen bonds, and as a result we're going to have a lower freezing point of that water. Good. And so the question is, give me some practical applications for lowering freezing point. This is where I talk about it in class, and then I take 7 minutes to try to drag ideas out of you. If we were in Minnesota, it would be easy. Why would we want water to freeze at a lower temperature? Because the roads, when they're icy, are dangerous. And so if we can add stuff to the roads in the form of salt or dirt or gravel or whatever, if we can add stuff to the roads, that's going to lower the freezing point of that water, and the roads stay water instead of turning into ice. So that's a huge example for us, and we'll come back and talk about that a little bit more in a second. The other one is boiling point elevation. So boiling point elevation is, it seems like if you add stuff and it lowers freezing point, it should also lower boiling point, but it kind of works to the opposite effect. Some of you have seen your mothers or fathers throw salt into boiling water, and you should ask them, why in the world are you throwing salt into that boiling water? And you can figure out whether they're lying or not, because most of them are throwing salt into the water because their parents threw salt into the water. If they say it's for flavoring, I always say if you want to taste the salt, then wait till you pull the food out of the boiling water and then sprinkle the salt on there. You'll taste it more. And if lots of times they're close. Lots of times you'll hear your parents will say it makes the water boil faster. And it's not that it makes the water boil faster as much as it makes the water boil hotter. And a result of it boiling hotter is that the food cooks faster, is the idea. And so the idea is this: here we have pure water, and all of these pure water molecules have direct access to the surface of the liquid as they move around. So you heat them up and they move toward the surface, and if you heat them up to boiling to 100 degrees, they have enough kinetic energy to escape that surface tension and turn into vapor. When you start to add stuff, and it doesn't matter what that stuff is, right? But if you start to add stuff into the water, what happens is these water molecules now don't have direct access to the surface of that liquid. So this water molecule, when you heat it up, it's trying to get to the surface, but it runs into that other solute particle, and that slows it down, and then it doesn't have the energy it needs to escape, right? And the more stuff you add, the more and more particles this thing's running into, and all these particles are slowing them down. And so how do you get them to escape the surface tension at all? You've got to make them move faster so that even when they run into these other particles along the way, they still have enough energy to break that surface tension. So the more stuff you add, the higher the boiling point has to become. Whatever the solvent is, we're using water because water is an easy example, and we use it most of the time anyway. But that's the idea. You have to speed those particles up because those other solute particles, you got to speed the water particles up because those other solvent particles are slowing down their escape from the surface. That makes sense? So that's boiling point elevation. You could add anything to the water and increase the boiling point. You could put sugar in there. My mother, when she used to cook, we'd say, "Mom, the pot's boiling over," when the water would start boiling over the top. And so she had a slab of butter, and she would take a butter knife and chop a piece off and throw it in there, and that butter would calm the water down. And then 3 minutes later, we're like, it's boiling over again. And she would slap another chunk of butter in there, and by the time it was meal time, we have a whole stick of butter in whatever we were eating. So it doesn't have to be salt necessarily. It could be butter or dirt or whatever. Don't eat dirt. Good. And so here are the applications. We're just talking about them for a couple minutes here, and then we'll do the calculations on the next video. So here are some applications. Salting icy roads is a huge one. I talk about here in San Antonio, we don't salt the roads. We throw dirt and gravel on the roads. And the reason is because dirt, when you throw it on the roads, if you throw dirt or sand or gravel into water, that dirt doesn't break apart. And so for every 1 particle of dirt we put in, we only get 1 particle dirt out. Good. If you live up north, lots of times you hear about them throwing salt on roads. What's the advantage of throwing salt on the roads is that there's a dissociation of this salt. So sodium chloride here breaks apart into sodium ions. We've talked about this earlier in this chapter. It breaks apart. For every 1 sodium chloride particle we put in, how many particles do we get out into solution? We get 2 particles into solution. It's not about what you're throwing in, it's about how much you're throwing in. And so the salt is going to have twice as many particles that are in solution, and therefore lower the freezing point of that water twice as much as throwing dirt. We don't need the temperature here in San Antonio to go much below freezing, the water temperature. And so we don't need to throw salt on the road. Salt's expensive. Dirt, everybody's got in their yard, and so it's easier to throw dirt and gravel. It's cheaper, and we don't need to lower the freezing point very much. But there are some places where they'll throw calcium chloride out on the road, and calcium chloride would break into a calcium ion and 2 chloride ions, and we would have 3 particles. It would triple the freezing point depression. And so we're going to talk about that when we look at calculations. You're going to have to do some more of these dissociations. Making ice cream, a lot of us have done this down here, where you have the bucket and the inner bucket kind of moves in a circle, and the outer bucket you fill with ice cream salt and ice. You are lowering the freezing point of that water on the outside in order to freeze the ice cream. But you want that bucket to be able to keep turning and mixing your ingredients. And so you don't want the outside to freeze solid, or else your bucket can't turn, right? I always tell people you can tell where you sit economically based on how you make ice cream at home. If you got one of those where you push the button and the bucket turns on its own, turns around, makes your ice cream for you, it's because you're rich. If you have one of the, some of us have those hand crank ones where you got to crank the bucket around a circle. You got to earn your ice cream, right? If you got one of those, you're middle class. And then some of you have your parents give you 2 Ziploc bags. In the inner Ziploc bag you put cream and sugar, and then the outer one you put ice in, and you zip them up, and they tell you to go out in the yard and you shake them until the stuff in the middle freezes. That is, it's because you're poor. And if you're me, when I was a kid, my mom used to tell us, bring them bags back inside and rinse them out. You're going to put a sandwich in them for lunch tomorrow. And so you can kind of tell where you sit. If you haven't ever made ice cream, now's the time. You got time off. Get some cream and some sugar and a couple Ziploc bags and some salt, and see if you can't make some ice cream. Look it up online. And the last one here is a good one, antifreeze in cars. In your radiator you put antifreeze because you don't want to put pure water in your car, because if it gets too cold, the water will expand and crack your radiator. If your car gets too hot, the water will expand and crack your radiator. So antifreeze adds stuff to the solution so that your car, if it gets below 0 or above 100, you don't have problems with your radiator. And then the last one there says fish and insects have built-in antifreeze. There's a reason the whales at the North Pole are swimming in that water that's below freezing and not dying, and it's because they have some built-in antifreeze to them. It's also funny, you think, well, how's the water below 0 up at the North Pole? Shouldn't it be all ice up there? And it's not. Why? Because we've added something to the water up there. That's salt water, and so that salt is causing the freezing point to lower. So that water is below 0, even though it's still liquid. We'll come back in the next video, and I'll show you some of these calculations, how we can actually figure out how much the freezing point lowers. See you then.